Okay, so here I'm gonna briefly talk about Euler's method, which hopefully is something you've seen before. It's just used to um, estimate solutions to differential equations. This is how we're gonna get test charges to move. So test charges are gonna have a position, a velocity, and an acceleration that are always gonna be changing due to kind of what's going on the screen. I just pulled up this slide from a slideshow that I made for another class, but we're just going to look at this one slide for now. So here, if I only have something moving in the y direction, so it's going to start at y equals 0 with a 0 velocity, but a negative acceleration. So you can imagine this is something that's like falling down. And then from here, I'm going to say on the very next frame, I want to add the acceleration to the velocity, not the velocity to the position. So because this is 0, this is just going to stay 0. But now that's negative. And my acceleration is not going to change. And so now in the next frame, I'm going to have a -2 velocity with a -1 position. In this slide here, I have like a force acting on it. So that's why my acceleration changes. And you can kind of see everything is kind of moving together. If Euler's method is something you've seen before, you might have only been looking at like you might just have like y and dy dx, and those are the only two things you were looking at. But now you kind of have your y, you have your dy dt, and you have your second derivative of position. So yeah, that's a short presentation on that. Let's get into actually building it. Okay. I just need to copy this over from the last video. Awesome. Okay, everything's good now. Okay, so I'm gonna start out by creating a test charge class. It's gonna be very similar to my charge class. So I'm just gonna start out by copying all that, and then I'll call it test charge. But I'm not gonna need a lot of this. So test charges don't have sliders, they can't be selected or dragged around. The radius of these is gonna, so I have test charges as kind of smaller in this simulation here, and so I'm gonna create a new variable called test charge radius, and I will stick this up here and say let test charge radius equal maybe 5 pixels, and test charge diameter is going to be 10 pixels, or just test charge radius times 2. Let's see. Okay. So I have that all taken care of. Yeah, they can't be selected, so I'm not going to need any of this. And they also don't have any text on them, so I can take out all of this. This diameter here is going to be my test charge diameter. Okay, cool. I have my test charge class. A few things I need to add to this would be I'm going to have this dot velocity, and that's going to start out as just a 0 vector. And I'm also going to have acceleration. I'm just going to, and that's also going to start out at 0. In order to display these, I have my display method here, and I'm going to need to kind of call that every frame, just like I have here. And I'm also going to store my test charges in a different array here, so I'll call it test charges. So I'm just going to have let test charges equal to an empty array. And then at the beginning, I'm just going to throw a single test charge into that. So I'll say test charges, and I'll push in a new test charge, and I'm going to give it a position as well as a charge here. The charge, let's go with like 0.1 or something. I'm also just going to shift this over a bit. Okay, cool. So I have my test charge on screen here. Let's check if I have any errors or anything. I'm looking good. Okay. So let's just see. Okay, so I talked about before I have position, velocity, and acceleration, and I'm just going to be kind of adding those together every frame to get it to actually move. So let's start with just velocity. So I'm going to say the natural thing to do might be to say that like this dot velocity, this dot position equals this dot position plus this dot velocity, but as you can see, I'm not sure. Okay, that should trigger an error, and I'm not sure if that's what's happening here, but that's happening because the addition symbol doesn't know how to add vectors together. So this is another reason why we're using vectors, is because they have this add function where I can just add two vectors together. So I'm going to do this by just saying this dot position dot add this dot velocity, and that's going to happen every frame. So I don't have any errors now, but you can see it's also not moving. That's because I have a 0 velocity here. So if I give this a velocity to start out with, you can see it's moving across the screen. Okay, cool. If I give it an acceleration, it should, before it was kind of linearly moving, so now it should kind of, well, I don't actually do anything with the velocity, okay. Let's do that. So this dot velocity, and I'm gonna add on the oh yeah, there it goes. Okay, so you can see it like exponentially kind of gets faster and just shoots out. Maybe. Okay, yeah, you get the idea. Cool. So now I'm gonna need to get back into my physics equations because I'm gonna be moving this due to the force acting on it. I think I have that, I guess you could use this equation over here, just multiply the Q over to the other side. So I have my E field, which I did that in the last video. Now I just need to multiply that by the charge of my test charge to get a force. And I also have like, you know, if I have F equals ma, where is it? F equals ma, my mass is in kilograms. I could just simplify this to be a 1, just for simplicity's sake. So then my force is directly proportional to my acceleration with no like coefficient or anything. Okay, that was a lot of talking. So let's do that. So to do that, I will say this dot acceleration is equal to my actually, let's not do that. Let's do this in the other function that we had. So I'm gonna rewrite my E field at position function to be like net force at position. So net force at position. And then I'll say this is gonna be my final force, and I'll create this into like a vector. It's just gonna be a 0 vector. And then I'm gonna go through here. Instead of adding stuff on this way, I'm gonna need to kind of use that add thing that we just talked about. So dot add. And then now I'm gonna have let's see. So before I just had like a magnitude, then like a numerical number, but now I need a vector. So I'm gonna need to kind of break down the vector created into, I'm gonna need to break down that number into the x and y components to create that vector. And so to do that, I'm going to need to use some trig. So I'm gonna, where is it? If I'm just down to like 1 charge on the screen, let's bring that back on. these two are lined up, so I should only have like an x component here, and like if it was further down, I would have both an x and a y component. So that's all just gonna come through trig. I've already worked it out for you, but I would advise you to try and work this out for yourself just to see where everything comes from. And so I'm gonna have a theta in this, and that's just gonna be the angle between the position, the point that I'm talking about here, and the position of my charge. So I'm gonna say p5 dot vector dot I'm gonna subtract the two, dot position and point. So that's all that's gonna do, is it's gonna give me, because my 0, 0 point is up here, and so I'm subtracting them to where it's basically, if you draw it out for yourself, hopefully it's gonna make more sense what I'm talking about here. So then I'm gonna have my force in the x direction and my force in the y direction, and these are gonna be just more trig. So I have my overall like magnitude here, and I have my theta value. So I will be multiplying my E field by, for the x, I'm gonna use cosine of theta, and then for the y, I'm just gonna use sine of theta. And then I will say, I'll reuse this variable here and say E field equals create vector, and I'll just put in my force dot x, not force dot x, the x component of my force and the y component of my force. So now I don't know if that's gonna work. Let's see. If I click, there's an error. E field at position not defined. Scope 7, line 70. Okay, where is this coming from? So I have, this should be fine. Okay, let's see. This, let me try and let's try and like break this down to like go kind of debug everything. So I'm just gonna log out different stuff as I go through this. Okay, so I'm not even getting to this theta here. So maybe, does this even run to begin with? Okay, that doesn't even run to begin with. Okay. Oh, I renamed my function. That, yeah, okay. That makes sense. Okay. So now I always have a 0 vector, which isn't what I wanted. So now let me try and kind of debug this to find where the problem might be. Okay, so I have an actual E field value just like before, but I guess my these might be where the problem is. Oh, yeah, my theta here is a vector, right? Yeah, I should have mentioned this before. So what I'm doing is I'm gonna move this down for now. Okay, so I have this triangle that's created right here, and I have this theta right here that I'm gonna be kind of trying to solve for. So all I did is I translated everything up and over some. So I'm still gonna have that exact same triangle here. But now I have this point here and I have this point here, so I need to get the angle between these two, which was what that theta was supposed to be. And to do that, P5 just has this very simple solution with vectors. I'll just say heading, so that's going to give me the direction that the vector is heading in. And okay, cool. So now I have something that makes more sense. I'm getting like a vector output. I'm kind of speeding through this because I don't want this video to be too long, but in here I can say that this dot acceleration is equal to net force at position, and I will just give it this dot position, which is the position of my test charge. And I'm also gonna comment out that when I log out the final force, now I need to, instead of logging it out, I need to return it. Okay. So you can see my I have something there and it just shoots out because my the numbers are just too big, kind of, because you saw before when I gave it an acceleration of like 1, it would still like zoom off the screen really fast. So what I'm gonna do is play around with my k value. Okay, here it is. So maybe if I shrink this down, yeah, you can see that's kind of better. Let's just make k 1 for now. Cool. And you can kind of see what's happening. This doesn't make sense because it's being attracted to a positive charge. So a really quick fix to that is I could just say I will just multiply this by -1 for now. And now I have a charge that kind of is moving away from that. Okay, this video is 17 minutes. I need to kind of cut it here. But play around with this. Hopefully you followed my very like all over the place logic, but yeah, I'll see you in the next video where we're gonna kind of improve on this. Yeah.